Okay, so today I'm going to tell you some old and new results on flat modules and amenable algebras. We'll work in the setting of functional analysis, our algebras and modules are not just algebras and modules and in the algebraic sense. In the first half of my talk, we'll consider Banach modules or Banach algebras. And in the second half of the talk, we'll consider more general topological modules over topological algebras. Let me start with some motivation. Suppose that G is a locally compact topological group. As usual, we equip G with the left higher measure. Just in case, if you are not familiar with such objects, you may assume that G is just a group, because any group can be considered as a locally compact group with a discrete topology. And this is already a good example of a locally compact group. So let's introduce some notation. If phi is a complex function on our group, and x is an element of the group, then we denote by phi x the translate of phi given by the following formula. Let's now give the following classical definition. The group G is amenable if there exists a bounded linear functional M on the big O infinity space, essentially bounded measurable functions, such that, first of all, it satisfies the following identity. Norm of M equals M of 1 and equals 1. And second, M is left invariant in the sense that the following property holds. So this holds for each phi from the big O infinity space and for each little x in the group. And if these properties are satisfied, then we say that M is a left invariant mean. On G. There are many equivalent definitions of amenability. For example, we can replace here the big O infinity space by another sufficiently big Banach space of bounded functions on G. For example, we can replace L infinity of G by the space CB of G of continuous bounded functions on G, and we get an equivalent definition. Amenable groups were introduced by von Neumann in 1929, and they form a very classical and well-known and well-studied classes of locally compact groups with numerous applications to various fields of mathematics. As for concrete examples, an obvious example is any compact group, because in this case, each bounded measurable function is integrable, and the integration functional is obviously an invariant mean. It is also true, but less obvious, that all abelian locally compact groups are amenable. And more generally, solvable groups are amenable. As for counterexamples or non-examples, Well, the simplest example of a group which is not amenable is a free group. Of at least two generators. The matrix groups SLN, GLN are also not amenable because they contain the free group onto generators as a discrete subgroup. I'm not going to tell you much about amenable groups. This, as I have already said, that is a very important class. You can find information about amenable groups in several books. For example, there is a well-known old book by Greenleaf. Invariant means on topological groups. There is also a book, a more recent book by Patterson, entitled Amenability. And there is also a good book by Pierre, Amenable Locally Compact Groups. Okay, let's now look at amenable Banach algebras. So suppose that A is a Banach algebra. In general, we don't assume our algebras that our algebras are unital. So in general, A has no identity. And all algebras will be over the field of complex numbers. The category of left Banach A-modules will be denoted like this. And similarly, we'll consider the category of right Banach A-modules and Banach A-bimodules. So these are categories of Banach modules. Suppose now that we have a Banach A-bimodule X. Then by definition, a bounded linear map D from A to X is derivation if it satisfies the usual Leibniz identity. For all A and B in our algebra. And we say that D is inner. D is inner if there is an element little x and x, such that D acts by the following rule. So we can now consider the space of all derivations from A to X. This is a vector space. And we can quotient out the vector subspace, which consists of all inner derivations. And the resulting vector space is denoted by H1 of AX, and is called the first continuous Hochschild cohomology of A with coefficients in X. In fact, the first continuous homology has higher dimensional analogs, which are defined as the cohomology groups of a certain standard complex, standard co-chain complex. So the cohomology groups of this complex are denoted like this and are called the continuous cohomology of A. In the pure algebraic case, the Hochschild cohomology was introduced by Hochschild in 1945. And a Banach algebraic version was introduced by Kamowitz in 1962. Okay, now let's observe that if A is a Banach algebra and X is a left Banach A-module, then the dual space X star has a canonical structure of a right Banach A-module. And the right Banach A-module structure is given by the following formula. If F is a functional and A is an element of our algebra, then the element, the functional FA, is given by the following formula. Similarly, if X is a right Banach A-module, then X star is a left Banach A-module in a canonical way. And if X is a Banach A bimodule, then X star is also a Banach A bimodule.
Извините, пожалуйста, у вас выключен звук на планшете?
Хороший технический вопрос. У меня выключен, да. Сейчас.
Ну ладно.
Я даже гляну, сейчас. Эхо, да, слышно?
Ну так, да.
Так, ну вот в Zoom выключен, и сам микрофон вроде тоже выключен. Сейчас гляну еще разок. Ну вот перечеркнутая у меня эта штука, да.
Ну, значит, непонятно. Ну ладно, не сильно.
К этому сижу, к ноутбуку, сейчас я чуть подальше от ноутбука сяду, и тогда, может быть, будет... Так. Так, попробуем.
Да не, ну не сильно, я просто... Вдруг... Ну, все хорошо.
Уже меньше, да? Нет?
Все хорошо, и было, в общем, тоже нормально.
Давайте попробуем. Если это будет плохо слышно, тогда я буду уже тут что-то думать, как это менять. Okay, we're now ready to define amenable Banach algebras. Well, the following definition is due to Barry Johnson. A Banach algebra A is amenable if for each Banach A bimodule X the first continuous Hochschild cohomology of A with coefficients in the dual bimodule X star vanishes. Or equivalently, more explicitly, this means that all derivations, I mean, of course, continuous derivations from A to X star are inner. Well, let's now see why amenable algebras are so called. What is the relation with amenable groups? So to answer this question, suppose that again that G is a locally compact group. We equip G with a left Haar measure. We consider the group Banach algebra L1 of G. So this is the usual big L1 space with respect to the Haar measure. And actually, this is a Banach algebra with respect to the convolution product. So if f and g are functions, L1 functions on G, then their convolution is given by the following formula. And it's the standard fact that L1 of G becomes a Banach algebra under convolution.
Why do we take dual here? So isn't that true that we can take double dual, and if we have some non-trivial derivation in space, then it is a non-trivial derivation in double dual?
We can consider double dual, and we get an equivalent definition. But in my view, this is not entirely trivial. This is a result by Frédéric Gourdeau. We can replace x star by x double star here. But of course, we cannot replace x star by x if we require that all derivations with values in all Banach modules are inner. Then we get a very small, very narrow class of Banach algebras. Sometimes such algebras are called contractible. And actually, the only example of such an algebra, the only known example of such an algebra, is a finite direct sum of full matrix algebras. Actually, there are numerous theorems which state that under suitable conditions on our algebra, if A is a contractible Banach algebra which satisfies some reasonable conditions, then it is isomorphic to a finite direct sum of full matrix algebras. For example, there are some results due to Yuri Vasilievich Selivanov of this type. And it's an open problem. If any contractible Banach algebra without any additional conditions is isomorphic to a finite direct sum of matrix algebras. This is an open problem.
But I don't understand. X is always a subspace of X double dual.
Yeah.
And if we have some non-trivial derivation on X, does it mean that we also have it on double dual or not?
Yes, but if our algebra is amenable, the derivation will be inner in the sense that it is implemented by an element in the double dual, but not in X itself. That's the difference.
Okay, thank you.
Okay, so now we are ready to answer to see the relation between amenable groups and amenable Banach algebras. So the relation is given by the following fundamental result, also due to Johnson. So if G is a locally compact group, then G is amenable as a group, if and only if the group Banach algebra L1 of G is amenable in the above sense. So this result explains why amenable Banach algebras are so called. And this result initiated the theory of amenable Banach algebras. So since then, amenability became one of the most important Banach algebraic properties. It is related to numerous problems in different fields of functional analysis. So this is probably one of the most well-studied and popular classes of Banach algebras. Okay. Oh, well, hey, as an illustration, let me formulate a couple of results which show relations between amenability and some other Banach algebraic properties. First of all, we need the following definition. a uniform algebra. Uniform algebra is a commutative Banach algebra. Commutative Banach algebra A, such that the Gelfand transform from A to C0 of X, where X is the maximal spectrum of A, is an isometry. In more down-to-earth terms, this definition can be given as given in the following way: a uniform algebra is a subalgebra in C0 of X, where X is a locally compact Hausdorff space, such that A is uniformly closed in C0 of X. Separates the points and has the property that for each point in X, there is a function in our algebra which doesn't vanish at X. So this is an equivalent definition of a uniform algebra. We now have the following result due to Sheinberg. Suppose that A is a uniform algebra. Then A is amenable if and only if A equals C0 of X. Well, the right to left implication, that is the fact that C0 of X is amenable, is already due to Johnson, but the criterion is due to Sheinberg. Another nice illustration of amenability is an amenability criterion for C-star algebras, which is due to Kohn and her group. So if A is a C-star algebra, then A is amenable, even only if it is nuclear. And nuclear means that for each C-star algebra B, there is a unique C-star norm on their algebraic tensor product. So it's a fact that in the general case, there can be many C-star norms on the algebraic tensor products. In particular, there is a so-called minimal C-star tensor norm and maximal C-star tensor norm. So equivalently, nuclear C-star algebras can be defined by the following equality. So the minimal C-star tensor product of A and B for each C-star algebra B is the same as the maximal C-star tensor product. Okay, so I hope that these few results, I mean Johnson's amenability theorem on group algebras, Sheinberg's theorem on amenable uniform algebras, and Kohn-High group criterion for C-star algebras, all these results already show that amenability is a nice and deep Banach algebra property. Okay, so my next goal will be to characterize amenability in terms of Banach homological algebra. This field of mathematics was initiated by Alexander Yakovlevich Helemskii in 1970. Another name for this field of mathematics is topological homology. Probably this is a little bit misleading, but it's nevertheless a standard name for this field. So let's give some definitions. Suppose that A is a Banach algebra. And suppose we have a short sequence of Banach A-modules, of left Banach A-modules. We say that this sequence is admissible if it is split exact in the category of Banach spaces. That is, if it has a contracting homotopy consisting of bounded linear maps. In other words, Y is essentially the direct sum of X and Z in the category of Banach spaces, but not in the category of Banach modules. Roughly, Banach homological algebra is a kind of relative homological algebra in categories of functional analysis, in particular in categories of Banach modules over Banach algebras. The difference is that the difference between this kind of homological algebra and pure homological algebra in the sense of Cartan and Ehrenberg is that in some places we have to replace exact sequences by admissible sequences. For example, let's give the definitions of projective modules, injective modules, and flat modules. So we say that a left Banach A-module P is projective if the home functor, where P is the first argument, it is fixed. So we consider home as a functor of the second argument. This functor acts from the category of Banach A-modules to the category of vector spaces. And we say that P is projective if this functor is exact, in the sense that it takes admissible, short admissible sequences, two exact sequences of vector spaces. An equivalent definition is as follows. Let's come back to the definition of an admissible sequence. So if we have such a sequence, then we say that the arrow from X to Y is an admissible monomorphism, and the arrow from Y to Z is an admissible epimorphism. So in other words, we say that a morphism from X to Y is an admissible monomorphism if it fits in a short admissible sequence of this form. And similarly, we define admissible epimorphisms. Now, coming back to projective modules.
Извините, один дурацкий вопрос. Там вот, можете дописать до конца определения в категории Банахового пространства, да? Spaces там должно быть.
Well, no, this is the category of Banach spaces.
Okay.
Spaces. Thank you. Okay, so now an equivalent definition of a projective Banach modules of a projective Banach module is as follows: a Banach module P is projective if this home functor takes admissible epimorphisms to surjections. Dually, we can define injective Banach modules. So we say that a Banach module J is injective if the home functor, where J is the second argument, this is the contravariant home functor, takes admissible sequences of Banach modules to exact sequences of vector spaces. Or equivalently, this means that this functor takes admissible monomorphisms to surjections. Well, so far, we see that these definitions are very similar to the classical definitions from pure homological algebra. And let's now define flat Banach modules. We say that the left Banach module F is flat. If the projective tensor product functor, which acts from the category of right Banach A-modules to the category of vector spaces, is exact in the same sense that it takes admissible sequences of Banach modules to exact sequences of vector spaces. Here, the tensor product, this symbol denotes the completed projective tensor product. So this is the standard tensor product of functional analysis. Okay, equivalently, F is flat if and only if this functor takes admissible monomorphisms to topological injective operators. And now we see a difference between this definition and the pure algebraic definition of a flat module. So the word topologically here is essential. Okay, so now let's discuss some standard facts of Banach homological algebra. Some standard facts which will be used in characterization of amenable Banach algebras given by Helemskii-Sheinberg. First fact is that the category of Banach A modules has enough projective. Enough projectives. This means that for each left Banach A module X, there exists a projective resolution. That is a complex of the following form, which is admissible, and such that all the modules P0, P1, and so on are projectives. Here is a sketch of proof. We let P0 be the following tensor product. So if we get now that X is a Banach A module, we just consider X as a Banach space, and we take the projective tensor product of A plus and X considered as Banach spaces. See here, A plus is the unitization of our algebra A. This module is easily seen to be projective. In fact, it has the stronger property, it is free, which means that for each Banach module Y, we have the following natural isomorphism. Here, B of xy denotes the space of all bounded linear operators from X to Y. Oh, seems that the pictures. Just a moment. Okay, now it is better. Okay, so we denote by P0 this tensor product. It is projective, and we have an admissible epimorphism from P0 onto X, given by the following formula. So this is easily seen to be admissible epimorphism. Now we take the kernel of this epimorphism, mu, and we iterate this procedure. So we take the projective tensor product of A plus and K, denoted by P1, and consider this the same multiplication map from P1 to K, and so on. So as a result, we get a projective resolution of X. This is a so-called bar resolution. Okay, so the category of Banach A-modules has enough projectives. And dually, it can be shown that the category of Banach A-modules has enough injectives. Which means that for each Banach A-module X, there exists an injective resolution, that is an admissible complex, an admissible co-chain complex of this form, such that all the modules J0, J1, and so on are injective. Okay, now by using this fact, we can define derived functors on the category of Banach A-modules. So if X and Y are left Banach A-modules, then we define the X functor, X of XY, as follows. First, we take a projective resolution P of X. Then we take the co-chain complex of morphisms from P to Y, and we take the nth cohomology. So here P is a projective resolution of X. Or equivalently, we can do the following. We can take an injective resolution of Y, take the co-chain complex of morphisms from X to this injective resolution, and take the nth cohomology. Here J is an injective resolution of Y. And we can also define the derived functor Tur. This is the derived functor of the tensor product. So if X is a right, now X is a right Banach A-module and Y is a left Banach A-module, we define the functor Tur as follows. We take any projective resolution P of X. We take the tensor product of P and Y, and we take the nth homology of the resulting chain complex. Or equivalently, we can do the same for Y, and the result will be the same. So here P is a projective resolution of X, and Q is a projective resolution of Y. So the definitions are similar to the classical definitions from pure homological algebra. And as in pure homological algebra, we have the following canonical isomorphism. The X0 functor is isomorphic to hom. And now a warning. In contrast to the classical homological algebra, the functor Tur0 is not the same as the tensor product. And this is essential. let me briefly explain the reason for that. If we have an exact sequence of the following theorem, and if we take the tensor product with a fixed module y, so we get the tensor sequence. In general, this tensor sequence is not exact. Even if we assume that, well, we can put 0 here, even if we assume that our original sequence is admissible, we cannot claim that the resulting tensor sequence is exact. And this is the main reason why the Tor-0 functor is different from the tensor product in general. However, the precise formula looks as follows. The tensor product is the Hausdorff space associated with Tor-0. So we must take the Tor-0 space and then quotient out the closure of 0. And the result will be isomorphic to the tensor product. However, the projective tensor product functor has a very close property. I mean that although this tensor sequence is not necessarily exact, the tensor product functor is co-kernel preserving. This is our second fact. First of all, let me recall how co-kernels look like in the category of Banach modules. If we have such a sequence of Banach modules, this is F and this is G, then G is a co-kernel of F, if and only if the image of F is dense in the kernel of G, and G is surjective. And it turns out that the projective tensor product is co-kernel preserving, namely if G is a co-kernel of F, then G tensor 1, so 1 is the identity map on Y, is a co-kernel of F tensor 1. In other words, this sequence here is not algebraically exact, but it's exact in some weak sense, in the sense that this arrow is always a co-kernel of this arrow. Okay, let's now discuss some more facts which are needed for proof of Helemskii-Sheinberg's theorem. Fact 3 is more or less standard. It is similar to the well-known result from pure homological algebra. Fact 3. A left Banach A-module P is projective if and only if the x1 functor, where P is in the first place, vanishes on the category of Banach modules. Dually, a Banach module J is injective even only if the x1 functor, where G is in the second argument, vanishes. And finally, left Banach module F is flat if and only if the Tor1 functor vanishes, and this is an essential feature of Banach homological algebra, the Tor0 is Hausdorff in its canonical topology. So this condition shows difference, essential difference between the classical, homological algebra for modules over rings and the Banach homological algebra. Another fact, also very rather easy, fact 4, which shows a relation between Hochschild cohomology and the derived functors. If A is a Banach algebra, then for each Banach A-bimodule X, the Hochschild cohomology of A with coefficients in X is isomorphic to the X functor taken in the category of Banach A-bimodules. So this is respective notation, where we have the unitization of A in the first argument and X in the second argument. Here's a sketch of proof. We take A plus, consider it in the category of bimodules, and take the bar resolution of A plus in the category of left Banach modules. The resulting complex turns out to be automatically a resolution of A plus, a projective resolution of A plus in the category of bimodules. So we can calculate X by using this resolution. And an explicit computation shows that the respective home complex is isomorphic to the standard cochain complex, which calculates the Hochschild cohomology. So the cohomology of these complexes are the same, and so the Hochschild cohomology is the same as this X functor. One more fact, fact 5, which is often proved in functional analysis courses. Sometimes it is referred to as Johnson's lemma. A short sequence of Banach spaces, say X of Banach spaces, is exact if and only if the dual sequence X star is exact. One more fact, fact 6, which is a special case of the joint associativity formula. Joint associativity. If we have two Banach modules, X and Y, X is a right Banach module and Y is a left Banach module, then the dual of their A module tensor product is isomorphic to the space of morphisms from X to Y star to the dual of Y. This is an easy exercise. And finally, the last lemma, fact 7. If we have two Banach modules X and Y, X n of x, y star. So we assume that x is a left A-module and y is a right A-module. So in this case, y star is a left A-module. So there is an isomorphism between this x space and the nth x from y to x star. Well, there are several ways of proving this. Probably the shortest way is to use the bar resolution. If we take the bar resolution of x and look at the Hom complex, which calculates the first x space, then this complex is easily seen to be isomorphic to the Hom complex from the bar resolution of y to x star. And that's it. So the first Hom complex calculates the first x group, and the second one calculates the second x. The complexes are isomorphic, so their cohomology is also isomorphic. Okay, now we can easily prove the following result due to Helemskii and Sheinberg. Banach algebra A is amenable in the sense of Johnson, if and only if its unitization A plus is a flat Banach A-bimodule. By the way, the history, as far as I know, was as follows. So Helemskii and his collaborators began to develop Banach homological algebra in 1970. Johnson's memoir on amenable Banach algebras appeared 2 years later in 1972. And when Helemskii and his colleagues obtained his memoir, so Johnson kindly sent his memoir to Helemskii, they understood that amenability is very close to their own research, I mean to the research of Helemskii and his school. And fairly soon, Helemskii and Sheinberg found an explanation of this similarity between Johnson's research and their own research. Now, well, because of the above facts, the proof will be very short. So let's recall the original definition of amenability. So A is amenable if and only for each Banach A-bimodule X. The first continuous cohomology group of A with coefficients in X star vanishes. Well, now we know this formula. We can now interpret the cohomology in terms of X. So we can write this space as follows. So this is X1 in the category of bimodules from A plus to X star. Or equivalently, because of fact 7, this is X1 again in the category of bimodules from X to A plus star. So we see that this X1 functor is identically 0 on the category of Banach A-bimodules. But this means precisely that A plus star is injective. And now to complete the proof, we need the following final fact. a Banach A-module X, or better F, is flat if and only if the dual module F star is injective. It's a very nice and very useful duality between flat modules and injective modules. By the way, the proof is very easy. We consider the tensor product functor by F. So by definition, F is flat if and only if this functor is exact, in the sense that it takes admissible sequences to exact sequences. Now we recall that a sequence of Banach spaces is exact if and only if the dual sequence is exact. So F is flat if and only if this functor is exact in the same sense. But because of the adjoint associativity, because of this formula, this functor is nothing but the home functor to F star. And this functor is exact by definition if and only if F star is injective. And now we can complete the proof of Helemskii-Sheinberg's result. So A plus star is injective if and only if A plus is flat in the category of bimodules. Okay. Well, this is the end of the first, I wanted to say the first half of my talk. Well, not the first half, but the first part of my talk. The second part will be, of course, much smaller because of time. Now let's consider more general locally convex algebras and more locally convex modules. So natural question is, can we extend the above results to more general topological locally convex algebras and modules? Let's introduce some terminology. All topological algebras I'm going to consider will be complete, locally convex, and having jointly continuous multiplication. Such algebras are often called algebras relative to the projective tensor product. Well, this is a complete locally convex algebra with jointly continuous multiplication. So it's impossible to pronounce this projective tensor product symbol. So if you don't mind, I'll call them just topological algebras. But when I say topological algebra, I always mean an algebra in this sense. Formally, this is nothing but an algebra in the tensor category of complete locally convex spaces equipped with the completed projective tensor product functor. Well, this, of course, this class of algebras is very big. It contains all Fréchet algebras. There is complete nonmetrizable topological algebras, and moreover, and of course, it contains all Banach algebras. As for non-normable examples, well, the algebras of continuous functions on sufficiently good topological spaces belong to this class. The algebras of smooth functions on real manifolds are Fréchet algebras, and moreover, so they are topological algebras in our sense. Algebras of holomorphic functions on complex manifolds belong to this class. Actually, they are Fréchet algebras. Algebras of compactly supported distributions on real Lie groups are natural examples of topological algebras, which are not metrizable, so they are not Frege algebras. And there are many other natural examples of such algebras. Well, when we consider such algebras, it is natural to consider topological modules over them. So by definition, a topological module, or more exactly, topological module relative to the projective tensor product over such an algebra, is a locally convex space, is a complete locally convex space equipped with a module structure such that the action of the algebra on the module is jointly continuous. The category of all left topological modules over A, where A is a topological algebra, will be denoted like this. And similarly, we can consider the category of right topological A modules and the category of topological A bimodules. Sometimes it is convenient to consider only those algebras and modules whose underlying vector spaces belong to some specific subcategory in the category of all complete locally convex spaces. So let's introduce some notation. We denote by CLCS the category of all complete locally convex spaces. And suppose that C is a full additive subcategory. We say that C is admissible if it satisfies the following conditions. First of all, C is stable under the projective tensor product. If X and Y are objects of C, then their projective tensor product is also an object of C. And second, it should be stable under topological direct summands. If X is an object of C, and if X is topologically isomorphic to the direct sum of two locally convex spaces, X0 and X1, then X0 and X1 are also objects of C. Now suppose that A is a topological algebra, and suppose that the underlying vector space, topological vector space of A, is an object of C. In this case, it is natural to consider the category of those topological A modules whose underlying topological vector spaces belong to C. And this category will be denoted like this. So this is a full additive subcategory in the category of all topological A modules. So we want to do some homological algebra in this category. This is indeed possible, and it was first observed about the same time when Helemskii developed his Banach homological algebra. So homological algebra in categories of locally convex modules was developed independently by Joseph Taylor in 1972, and by Keeley and Verdier in 1971, if I'm not mistaken. So here are some good news about this category. First of all, this category has enough projectives. And the proof is identical to the proof of the respective fact for Banach modules. As a corollary of this fact, we can define the derived functors x and tor. So they exist. Well, this is good. So we can develop some basic tools of homological algebra in this category. However, let's now look at some bad news about the same category. Actually, there are two groups of bad news. Some bad news are bad for all categories, or all good categories of non-normable locally convex modules. And other types of bad news are bad for non-metrizable locally convex modules. First of all, let's look at some bad properties of this category in the case where C is different from the category of Banach spaces. So this will be bad even if C is the category of Fréchet spaces. First of all, in general, this category doesn't have enough injectives. And moreover, there are many very good Fréchet algebras such that this category has such that the only injective object of this category is zero. So this holds for many algebras, for example, of algebras of smooth and holomorphic functions, for some of their non-commutative analogs. This is bad fact number one. So I observed this about a little bit more than 20 years ago. Another bad news, which was observed already by Taylor in 1972, and it looks as follows: if X is a left Banach, if X is a left topological A module in the category of A mode of C, then in general the dual module X star is not the object of the category of right topological A modules. And here are some reasons for this. First of all, it can happen that the underlying locally convex space of X star is not an object of C. So a typical example is the category of Fréchet spaces. So, by the way, when I take the dual, I always mean that the dual is equipped with this so-called strong topology, that is the topology of uniform convergence on bounded sets. If C is the category of Fréchet spaces, then it is a standard and simple fact that the dual of a Fréchet space is itself a Fréchet space, if and only if X is a Banach space. So the dual, in other words, the dual of a non-normable Fréchet space is not metrizable. The second reason why we cannot take the dual modules is that in general X star is not complete. In fact, it is complete in many good cases. For example, the strong dual of a Fréchet space is complete, but in general, it is not complete. And probably the most essential reason is that the canonical action of A on X star is not jointly continuous. So X star is not a topological module in our sense. The action is not jointly continuous. In some good cases, it is separately continuous. So X star is still a topological module in some weak sense. But nevertheless, this action in general is not jointly continuous. Let's now look at some bad properties of the category of topological A modules in the case where our base category C consists of non-metrizable locally convex spaces. So property 3, yeah. If you have a short sequence of spaces from C, then the sequence is exact, and the exactness of the dual sequence in general are not equivalent. In other words, Johnson's lemma fails. So this is still true for Fouché spaces, but this is not true for more general locally convex spaces. Bad news number 4, the joint associativity fails in general. In other words, if we take the dual of the tensor product, this is not the same as hom from X to Y star. And finally, bad news number 5, which is closely related to flatness, is that the co-kernels in our category C in general are not surjective. Let me explain this in more detail. So suppose we have a following diagram in our categories of A modules. Now I consider the category of all complete locally convex A modules. So G is a co-kernel of F if and only if the image of F is dense in the kernel of G. The image of G is dense in X3, and G is an open map onto its image. But in general, I don't claim that G is surjective. Well, why is it bad? This is briefly, this is bad because our naive definition of a flat modules is not good in the nonmetrizable case. Let me explain this in some more detail. So let's try to adopt the following a bit naive definition of a flat module. We say that left A module F in our category A mode of C is flat if the tensor product functor, projective tensor product, is exact in the same sense as before. So it takes admissible sequences of right A modules to exact sequences of vector spaces. So let's draw a respective picture. So we have an admissible sequence of right A modules. And we consider the respective tensor sequence. So where are the obstructions for the flatness of F? By the way, it's interesting to compare this with the pure algebraic case. In the purely algebraic case, where we consider just modules over algebras, which are not equipped with any topology, In the algebraic case, the abstractions for flatness of F sit only at the first position. I mean here. In other words, in the algebraic case, the sequence is always exact here and here. And F is flat if and only if the sequence is exact here. That is, if and only if this arrow is injective. This is a standard fact from classical homological algebra. In the Banach case or in the Piszczek case, the situation is a bit different. So we know that in general, this tensor sequence is exact here. Oh, sorry, exact here. But in general is not exact here. We only know that the image of this arrow is dense in the kernel of this arrow. And we know that F is flat if and only if this first arrow is topologically injective. And by the open mapping theorem, this means precisely that this arrow is injective and its image is closed. So we may say that in the Banach case or in the Piszczek case, the abstractions for flatness sit not only here, but also here. This is not so good as in the algebraic case, but it is still quite manageable. But in the general case, the obstructions are everywhere. And hypothetically, it can happen that a module F, there can exist a module F which is which behaves like a flat module, and which should be flat by some reasons, but which is not flat formally for the only reason that this arrow is not surjective. So the obstructions are not in the right place. So these arguments show that our naive definition of a flat module is not very convenient when we work with nonmetrizable locally convex algebras and modules. And in fact, indeed, if we try to prove something by using this definition, we can do this only in the metrizable case. In the non-metrizable case, this definition is not convenient. I have to finish. Well, if you give me some more time, maybe 5 minutes, I'll briefly explain what is, in my view, the correct definition of a flat topological module. This will take, I hope, at most 5 minutes, and then I'll finish.
Okay.
Thank you. Okay, so we will need the following category theoretic definition. Let's discuss strictly exact sequences. So suppose that A is an additive category. Suppose we have a short sequence in A. We say that the sequence is strictly exact. So suppose this is F and this is G. So we say that the sequence is strictly exact if F is a kernel of G and G is a co-kernel of F. Here are some concrete examples. Example 1. If A is a billion, for example, if A is the category of all modules over an algebra or over a ring, then a sequence in A is strictly exact if and only if it is exact. Example 2, which is probably the most important for us. Suppose that A is the category of complete locally convex spaces. Then our sequence is strictly exact, even only if the following conditions hold. First, F is topologically injective. Second, the image of F equals the kernel of G. So we have algebraic exactness at Y. The image of G is dense in Z. And finally, G is an open map onto its image. So this is a characterization of strictly exact sequences in the category of complete locally convex spaces. This is more or less equivalent to our characterizations of co-kernels in this category, which we discussed earlier. Maybe this can be also defined in slightly different terms. Our sequence, the sequence is strictly exact in the category of complete locally convex spaces, even only if X is identified with, is topologically identified with the closed vector subspace of Y, and Z is identified with the completion of the quotient of Y modulo X. So it's essential that we have to take the completion of the quotient, because in general, if we work with nonmetrizable spaces, the quotient of a complete space modulo a closed subspace is not necessarily complete. And this is the reason why the co-kernels are not in general surjective. And example 3. If A is the category of Banach spaces or the category of Frichet spaces, then the sequence is strictly exact A, even only if it is strictly exact in the category of all complete locally convex spaces, and even only if it is algebraically exact. It is exact in the category of vector spaces. This is a simple exercise on the open mapping theorem. Okay, now we can give our modified definition of a flat module. So suppose that C is an admissible subcategory of the category of complete locally convex spaces. Suppose that A is topological algebra such that the underlying space of A is an object of C. We say that a left topological A module F is flat if the projective tensor product functor takes admissible sequences of right A-modules to strictly exact sequences of complete locally convex spaces. So if we look again at example 3, we see that if C is the category of Banach spaces or the category of Fréchet spaces, then this definition is consistent with our earlier definition of a flat Banach module or of a flat Fréchet module. But in the general case, if C consists of nonmetrizable spaces, this definition is not the same as before, so it is a bit different, at least formally. And my point is that this is the correct definition. Unfortunately, I have no time to explain this in more detail, but roughly the point is that many results about flat modules, which are known to be true in the context of Banach modules, or more generally in the context of Fréchet modules, are still true in the categories of more general non-metrizable locally convex modules if we give this modified definition of flatness. In particular, for some important categories of non-metrizable spaces, namely for the category of, for example, for the category of complete barreled DF spaces. Unfortunately, again, I have no time to define them. There is an analog of Helemskii-Sheinberg's result, namely an algebra in this category is amenable in Johnson's sense, if and only if its unitization is a flat, in this sense, flat bimodule. And also by using this definition of flatness and the related definition of amenability, it is possible to characterize amenability in a rather interesting class of algebras, the so-called co-echelon algebras. These algebras consist of sequences. The multiplication is pointwise, and the sequences should satisfy some growth conditions at infinity. So a typical example of such an algebra is the algebra of sequences of polynomial growth, or the algebra of germs of holomorphic functions at a point of a complex plane equipped with the so-called Adamar multiplication. So the Adamar multiplication of two holomorphic germs is a holomorphic germ whose Taylor coefficients are just the component-wise products of the Taylor coefficients of the respective functions. So if we consider the class of co-echelon algebras, then it turns out that it is possible to give an explicit amenability criterion for such algebras. And this was done in our recent joint preprint with Krzysztof Piszczek from University of Poznan. Well, probably that's all I wanted to tell you today. And sorry for, well, I should have finished long ago, 20 minutes ago. So I'm sorry about that.